To build the chip in your pocket, we have to hit a falling drop of tin with a laser twice, 50,000 times a second, in a vacuum harder than deep space. This is not a description of a sci-fi weapon or a particle physics experiment at CERN. This is a commercial manufacturing process. It is the only way humanity currently has to produce the advanced microprocessors that power our modern world. In a small town in the Netherlands, a company called ASML has built what is arguably the most complex machine ever created by human beings. They call it an extreme ultraviolet lithography system, or EUV for short. To the rest of us, it is the atomic printer. It is a machine that operates at a scale where the very laws of classical physics begin to break down, where light behaves in ways that seem impossible, and where engineering precision is measured in the width of a single atom.
For decades, the semiconductor industry followed a predictable path known as Moore's Law. Gordon Moore, the co-founder of Intel, observed in 1965 that the number of transistors on a microchip would double approximately every 2 years. For 50 years, we kept pace. We shrank transistors from the size of a fingernail to the size of a red blood cell, then to the size of a virus. But by the mid-2010s, we hit a wall. The light we were using to print these chips, known as deep ultraviolet light, had a wavelength of 193 nanometers. When you are trying to print features that are only 7 or 5 nanometers wide, using a 193 nanometer light source is like trying to draw a fine line with a thick crayon. We used tricks like immersion lithography, where we shone the light through water to refract it, but eventually the tricks ran out. We needed a smaller crayon. We needed extreme ultraviolet light.
EUV light has a wavelength of just 13.5 nanometers. It is so close to the X-ray spectrum that it behaves unlike any light we have ever used in manufacturing. It is difficult to create, nearly impossible to reflect, and it is absorbed by almost everything, including the very air we breathe. To harness this light, ASML had to rethink the entire concept of a printer. They had to build a machine that doesn't just push the boundaries of engineering, but one that defines them. This is the story of how we learn to manipulate the fabric of reality to keep the digital revolution alive. The journey starts with a drop of tin. In the heart of the EUV machine, a generator ejects tiny droplets of molten tin, each about 30 micrometers in diameter, at a speed of 70 meters per second. These droplets fall through a vacuum chamber. As they fall, a high-power CO2 laser fires a pre-pulse. This pulse doesn't vaporize the tin. It hits the droplet with just enough energy to flatten it into a pancake shape. This is crucial because a sphere has a low surface area to volume ratio. By flattening it, we increase the surface area for the next step. A few microseconds later, a second, much more powerful main laser pulse strikes the flattened tin pancake. The energy is so intense that the tin instantly vaporizes into a high-energy plasma. This plasma reaches temperatures of nearly 500,000 degrees Celsius, which is significantly hotter than the surface of the sun. In this state, the tin atoms shed their electrons and emit photons at exactly 13.5 nanometers. This is our EUV light source. But there is a catch. This happens 50,000 times every single second. The timing must be perfect. If the laser is off by even a fraction of a microsecond, or if the droplet is a few nanometers out of place, the process fails. This happens continuously, 24 hours a day, inside a machine that costs over $200 million.
Once we have created this EUV light, the next challenge is moving it. In traditional lithography, we use glass lenses to focus light, but EUV light is different. Because its wavelength is so short, it is absorbed by glass. If you tried to use a standard lens, the light would simply disappear into the material, heating it up but never reaching the silicone wafer. In fact, EUV light is absorbed by almost every material on Earth. Even air absorbs it, which is why the entire internal works of the machine must be kept in a vacuum more pristine than the environment surrounding the International Space Station. Since we cannot use lenses, we must use mirrors, but these are not ordinary mirrors. A standard household mirror reflects about 90% of visible light using a simple silver coating. For EUV light, a silver coating would be useless. Instead, ASML partnered with the German optics company Zeiss to create the most precise mirrors ever manufactured. These mirrors are made of alternating layers of silicon and molybdenum, each only a few nanometers thick. There are about 40 to 50 of these pairs in a single mirror. This structure is called a Bragg reflector. It uses constructive interference to reflect the EUV light. The precision required for these mirrors is mind-boggling. The surface must be so smooth that the largest deviation is no more than the width of a single atom. To give you a sense of scale, if one of these mirrors were expanded to the size of the United States, the highest bump on its surface would be less than a millimeter tall. If the mirror is even slightly imperfect, the EUV light will scatter and the chip's features will be blurry. This level of polishing takes months and requires specialized robotic systems and ion beam etching to achieve atomic-level perfection. Even with this incredible engineering, these mirrors only reflect about 70% of the EUV light that hits them. The rest is absorbed as heat. In a system with several mirrors, the light loses energy at every bounce. By the time the light reaches the silicon wafer, only a small fraction of the original energy remains. This is why the initial tin plasma light source has to be so incredibly powerful. We are fighting a war against the absorption of light itself. While the light source and the optics are the soul of the machine, the wafer stage is its mechanical muscle. The silicon wafer, the disk upon which the chips are printed, must be moved with terrifying speed and precision. As the EUV light patterns the circuit onto the wafer, the stage moves the wafer back and forth. It accelerates at several Gs, faster than a fighter jet taking off. Yet it must stop at an exact position with a precision of less than a nanometer. Think about that. We are moving a heavy piece of equipment at high speeds and stopping it within the width of a few atoms. To achieve this, the stage floats on a bed of magnets, using a technology called maglev to eliminate friction. It is controlled by sensors that measure its position thousands of times a second using laser interferometry. Any vibration, even the distant rumble of a truck on a nearby highway or the footsteps of a technician, could ruin the alignment. The machine is housed in a massive concrete bunker with specialized dampening systems to isolate it from the rest of the world. Inside the machine, another silent battle is being fought, the battle against contamination. Because EUV light is so easily absorbed, even a single molecule of carbon or a tiny speck of dust can block the light and create a defect on the chip. But the process itself creates debris. When the laser hits the tin, it doesn't just create light, it creates tin debris. ASML engineers had to develop a system using a flow of hydrogen gas to act as a buffer, pushing the tin particles away from the sensitive mirrors. This hydrogen is then ionized into a plasma to clean any carbon that might settle on the optics. It is a self-cleaning, self-contained ecosystem, operating at the edge of physical possibility. Why do we go to all this trouble? The answer lies in the concept of nanotechnology and the demands of modern computing. As we move into the era of artificial intelligence, 6G communication, and autonomous vehicles, the demand for processing power is exponential. To make a chip more powerful, you need more transistors. To fit more transistors, they have to be smaller. With EUV lithography, we can now print features that are 3 nanometers or even 2 nanometers apart. For context, a strand of human DNA is about 2.5 nanometers in diameter. We are literally printing machines at the scale of biology. This capability has turned ASML into the most important company you have probably never heard of. Based in Veldhoven, Netherlands, ASML doesn't make chips, they make the machines that make the chips. They have a 100% market share in EUV lithography. If ASML stopped shipping machines tomorrow, the progress of global technology would effectively grind to a halt. There is no plan B. No other company on Earth has the combined expertise in plasma physics, extreme optics, and mechatronics to build these systems. This has placed ASML at the center of a global geopolitical struggle. Semiconductors are the new oil. They are the fundamental resource of the 21st century. Because ASML's EUV machines are so critical, they have become a tool of international diplomacy and trade restrictions. The supply chain for a single machine involves thousands of suppliers from across the globe, from specialized chemicals in Japan to high-power lasers from Germany and light sources from the United States. It is a monument to global cooperation, yet it is also a point of extreme vulnerability. As we look toward the future, the engineering challenge doesn't get any easier. ASML is already rolling out the next generation of these machines, known as High-NA EUV. The NA stands for numerical aperture. By increasing the numerical aperture of the optics, they can focus the EUV light even more tightly, allowing for even smaller features. These new machines are even larger, more expensive, and more complex. They require even more power and even more precise mirrors. We are reaching a point where we are no longer just printing circuits. We are manipulating individual atoms. At this scale, we have to deal with effects like stochastic noise, where the random behavior of individual photons can cause errors in the printing process. We are fighting against the statistical nature of the universe itself. But this is the core of semiconductor engineering. It is a constant battle against the limitations of the physical world.
The EUV machine is a testament to what humans can achieve when we stop looking for magic and start looking at the math. There is no sorcery in the tin droplet, only the precise application of kinetic energy and atomic physics. There is no miracle in the mirrors, only the relentless pursuit of surface perfection through chemistry and mechanical engineering. When you look at the smartphone in your hand, you aren't just looking at a piece of consumer electronics. You are looking at the end product of a process that involves artificial suns, atomic scale mirrors, and vacuums harder than space. It is the pinnacle of the industrial age and the foundation of the digital age. It is a machine that bridges the gap between the world we can see and the world of the infinitely small. As we push further into the nanometer gap, the challenges will only grow. We will face the limits of materials, the limits of heat dissipation, and the limits of quantum tunneling. But if the history of the atomic printer has taught us anything, it is that impossible is simply a temporary state of engineering.
Every time we think we have reached the end of Moore's Law, a group of engineers finds a way to squeeze a few more billion transistors onto a piece of silicon. They do it by mastering the behavior of light, the properties of matter, and the precision of motion. They do it by proving, over and over again, that the most incredible things in our world are not magic. They are the result of rigorous, uncompromising, and brilliant engineering. The nanometer gap is small, but the ingenuity required to bridge it is the greatest achievement of our time. As we move into 2026 and beyond, the roadmap for semiconductors points toward even more exotic techniques. We are looking at gate-all-around transistors, backside power delivery, and 3D stacked integrated circuits. All of these innovations rely on the foundation laid by EUV lithography. The machine in Veldhoven will continue to pulse, hitting tin droplets 50,000 times a second, firing its lasers and reflecting its invisible light to carve the future of humanity. We are no longer just using tools to build our world. We are using the fundamental forces of the universe to print it. The atomic printer is more than a machine. It is the bridge to the next era of human civilization, where the distinction between the digital and the physical becomes thinner with every passing nanometer. And as long as we keep pushing, as long as we keep refusing to accept the impossible, the light of the EUV will continue to illuminate the path forward. In the world of not magic, this is as close to perfection as we have ever come. This has been the story of ASML and the engineering of the nanometer gap. A story of how we turned a falling drop of tin into the most powerful tool in history. A story of science, engineering, and the relentless pursuit of the small. Because in the end, it's not magic that builds the future, it's engineering.